Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is
Yeah.
ProfSam.com.
Hello?
Today we'll be undertaking a deep dive into Coulomb's law. It's, the essential foundational principle from Unit 1, electric charges and fields.
A really important one for the exams.
Absolutely. Our mission is to give you a simple, exam-safe explanation that you will, I hope, retain and apply successfully.
Okay, I'm ready.
So let's start with a simple, everyday observation.
Right.
You have surely done this experiment. You rub a balloon vigorously on your hair and then bring it near some small, light pieces of paper.
Yes, and they jump up and stick to it.
Exactly. Now, we know this involves static electric charge, but the real question is, how do we actually calculate the exact force of attraction needed to lift that tiny piece of paper?
It just seems like magic, doesn't it? We can see the force, we can see the paper jumping, but how to put a precise number of value on that invisible pull?
Precisely. And this is where the genius of Coulomb's law becomes absolutely critical.
Okay.
Now, you might intuitively think, well, if I make the charge on the balloon twice as strong, the attractive force will also simply double.
A linear relationship. Seems logical.
It does, but that's not how it works. In reality, governed by Coulomb's law, it's more complex.
Yeah.
If you double the charge on the balloon, and somehow you could double the induced charge on the paper, the force doesn't just double.
It does more.
It quadruples.
Wow. Oh, yeah.
This nonlinear, this multiplicative behavior is a key hallmark of electrostatics, and we really must understand the mathematical reason behind it.
So that's what the law explains.
That is what the law explains. So, okay, let's unpack this relationship. At its heart, Coulomb's law is simply the fundamental mathematical rule that quantifies the electrostatic force between any two stationary point charges.
Okay, so it's a formula for that force.
Yes, that's the core idea. Fundamentally, this force depends on three things. First, the quantity of charge on the first object.
Right.
Second, the quantity of charge on the second object.
Right.
And third, well, the distance separating them.
That makes sense. Charge and distance.
And what's fascinating here is that, this law had to be discovered to move physics forward. For a long time, people only understood static electricity through observation.
Just seeing things attract or repel.
Exactly. Action at a distance. Coulomb gave us the tool to stop just observing and start predicting precisely how strong the force would be.
That's a huge step.
It is. Now, to anchor this idea, let's think back to Class 11 of physics. This law is almost identical in its structure to Newton's law of universal gravitation.
Oh, right. The one where F is proportional to m1, m2 over r squared?
You remember it perfectly. F is proportional to the product of masses divided by the square of the distance.
So we have the same inverse square relationship with distance here, too.
Precisely. But here is the major conceptual difference, and it's a big one. We can think of gravity as a one-lane highway.
A one-lane highway?
Yes, where mass always attracts.
Yeah.
There's only one direction for the force. But electricity, because charge comes in two types, positive and negative, is like a two-lane highway.
Ah, so it can go both ways.
Exactly. The force magnitude follows the same inverse square rule. But the force itself can be attractive if the charges are opposite, or it can be repulsive if the charges are the same.
That is a great way to put it. So the math for distance is similar, but the physics, the actual nature of the force, is very different.
Absolutely. Now, let's try a simple mental image to lock in that inverse square relationship, that one by r squared.
Okay.
Picture two charged spheres, and they are surrounded by invisible lines of force, kind of like ripples spreading out in water.
Right.
Close to the sphere, the circles are very dense, very close together. That signifies a powerful force field.
Okay. Dense means strong.
Yes. And as you move away, the lines become sparser and the force weakens very quickly. Now, if you take those two spheres and you have the distance between them,
The lines would get denser.
they become 4 times denser, and the force quadruples instantly. The change is exponential, not linear.
I see how that visualizes the 1 by r squared factor.
Good. Now, that is the perfect question that bridges the conceptual part to the more technical definition. To turn that proportionality, F is proportional to Q1, Q2 by R squared into a proper equation, we need a proportionality constant.
A constant, okay.
We usually call it K. And this K is what sets the scale for the electrostatic interaction in our universe.
So K is the key to the actual value.
It is. So now that we've introduced the constant K, Let us look at how Ensert formally defines this.
Yeah.
Could you please read the scalar form of Coulomb's law exactly as it is written in the textbook?
Of course. It says, the constant k in equation, 1.1, is usually put as k equals 1 upon 4 pi epsilon naught for later convenience, so that Coulomb's law is written as F equals 1 upon 4 pi epsilon naught times Q1 Q2 upon r squared.
Thank you.
That constant looks quite intimidating. What exactly is that epsilon naught, and why is A broken down into that 1 by 4 pi epsilon naught
A
form?
very important question. This is critical for understanding the mechanics of charge interaction. So let's address epsilon naught first. Epsilon naught, written as S, is called the permittivity of free space.
Permittivity.
Yes. Think of permittivity as a measure of how strongly the medium permits or allows an electric field to exist within it.
So it's about the medium itself.
Exactly. A higher permittivity means the medium is better at screening or resisting the field, which weakens the force between the charges. Epsilon naught is the value for a vacuum or free space, which has the minimum possible resistance.
I see. And the whole 1 by 4 pi part.
That's mainly for mathematical convenience in SI units, especially when we move from simple point charges to more complex field problems later on. It simplifies other equations.
Ah, okay.
Now, regarding the overall value of K,
Yeah.
in SI units, K is approximately 9 times 10 to the power of 9 Newton meters squared per Coulomb squared.
9 times 10 to the power of 9. That's a huge number.
It is an enormously large number.
9 billion. I can see now how that explains the strength of the force.
Indeed. This immense value is the fundamental reason why electrostatic forces are so much stronger than gravitational forces.
Right.
To give you a deeper insight, this huge constant K is why matter, as we know it, is stable. The positive nucleus and the negative electrons in an atom are held together by this immense electrostatic force. If K were smaller, atoms would just fall apart.
And chemistry and life wouldn't exist.
Precisely. Coulomb's law is like the glue of the physical universe, and K determines the strength of that glue.
Wow.
Okay, so now let us break down the mathematical relationship F equals K times Q1 Q2 by R squared into 4 critical steps for solving problems.
Steps. Good.
First, we examine the product of charges, the Q1 Q2 part. The force is directly proportional to this product. This is where that multiplicative effect we discussed earlier comes from.
Okay.
If you double Q1 and you triple Q2, the force increases by a factor of 6.
Not 5. 6 multiplied.
Correct. So we always look at the product, not the individual increase. Second, the inverse square law, 1 by r squared.
The ripples.
Exactly. The force is inversely proportional to the square of the distance. Remember, small changes in separation cause massive changes in force.
Got it.
Third, and this is very important for problems, determining direction. You don't need 2 separate equations for repulsion and attraction.
The math tells you.
The math itself tells you the direction. It's all in the sign of the product Q1, Q2. If the product is positive, that means like charges, right? Positive times positive or negative times
The
negative.
force is repulsive.
Correct, a push. And if the product is negative, unlike charges.
It's attractive. A pull.
Perfect. The math handles it all. And finally, number 4, we must remember that this is a central force.
Central force.
Meaning the force acts exclusively along the line connecting the 2 charges. It doesn't act sideways or at an angle. It's always centered on that joining line.
Okay, those 4 steps seem clear.
I hope everything is clear so far. This concept explainer is from ProfSam.com.
Okay.
Now let's apply these steps to a very minimal worked example. This really helps to see the power of the force. Suppose we have a charge Q1 equals plus 3 times 10 to the minus 6 coulombs.
So 3 microcoulombs.
Yes. And charge Q2 is plus 4 times 10 to the minus 6 coulombs. Both are tiny charges. They're separated by a distance r of half a meter.
Okay, 0.5 meters.
Right, so step 1. Are they like or unlike charges?
Both are positive, so they're like charges. The force must be repulsive.
Excellent. Step 2. We use the formula F equals K times Q1 Q2 over R squared, using K as 9 times 10 to the power of 9.
Okay.
If you perform that calculation, you find the resulting force F is 0.432 newtons.
0.432. That's actually astonishing.
Why do you say that?
Well, we're using microcoulomb charges, which are tiny, and separating them by half a meter, yet the force is definitely measurable, about the weight of, say, 44 grams.
Exactly. That really drives home how incredibly large that constant K is. Even the smallest measurable charges generate significant forces.
It makes sense now.
And understanding this precise inverse square relationship is not just for 2 charges. It unlocks the next major topic in our unit, the principle of superposition. Superposition simply uses Coulomb's law again and again to calculate the total force exerted by multiple charges on a single test charge.
Ah, so you just add up the forces from each one.
Vectorially, yes.
Mm.
If you understand the force between two, you can solve for the force from 20.
Okay.
Now, students, let us discuss the three silent killers. These are the misconceptions that frequently appear in exams and unnecessarily reduce your marks.
This is important.
Very. Misconception 1, the distance effect is linear.
I can see how students would think that.
Yes, the wrong idea is, if I move the charges 2 times farther away, the force decreases by half. It's a common mistake. The correct understanding is that the force follows the inverse square law.
So double the distance, the force becomes 1/4. Triple the distance, it becomes 1/9.
Exactly.
So if I see a question where the charges are brought, say, 4 times closer, I must instantly think of force squared, so the force increases by 16 times, not just 4 times.
That is the required quadratic thinking. Perfect. Misconception 2. Charges only attract or repel mysteriously. The wrong idea is that opposite signs attract, same signs repel, is just some arbitrary rule you have to memorize.
But it's not arbitrary.
Not at all. The correct understanding is that it is purely mathematical. The sign of the product Q1, Q2 determines the direction. A positive product means repulsion. A negative product means attraction.
So the hook to remember is sign of product determines push or pull, not arbitrary, mathematical.
Exactly right. And finally, misconception 3, Coulomb's law fails if charges are moving.
Because we call it electrostatics.
That's the source of the confusion. The wrong idea is, since we study electrostatics, the law is only valid for charges strictly at rest.
And the correct idea.
The correct understanding is that Coulomb's law defines the fundamental electric force component regardless of motion. When charges move, additional magnetic forces arise, which we study later.
Ah, so the electric part of the force is still there.
Yes, and it's still calculated using Coulomb's law. So the takeaway is, Coulomb for electric forces, moving charges only add magnetic forces.
That clears it up.
Good. Now let's move to some memory anchors, designed to seal this concept permanently in your mind, especially during exam pressure.
Okay, mnemonics.
First, remember 3 key letters. CQR.
CQR.
C for Coulomb, Q for quadratic, representing that inverse square dependence, and R for repel or reattract, depending on the sign. CQR.
Simple enough.
Second, a simple phrase to memorize. Charge product over distance squared, push if same, pull if opposite.
That summarizes the whole law in one line.
It does. And third, a physical gesture to internalize the direction. Next time you're calculating a force, hold up 2 clenched fists.
Okay.
If the charges are the same, push your fists apart sharply. That's repulsion.
Right.
If they're opposite, pull them together. That's attraction. The imaginary distance between your hands is R.
Oh, that's a good way to physically feel the direction.
It helps you instantly recall the force direction and its central nature.
I like that.
Okay, so let's quickly summarize the 3 essential factual takeaways for your exams.
The 3 main points.
First, Coulomb's law quantifies the electrostatic force between 2 point charges using the formula F equals K times Q1 Q2 over R squared.
Point 1, the formula.
Second, the force is always directly proportional to the product of the charges and, crucially, inversely proportional to the square of their separation.
Point 2, the proportionality.
And third, the force is a central force acting along the line joining the charges. This force is attractive if charges are opposite and repulsive if they are the same.
Point 3, the direction. Got it.
Excellent. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROFSam, right?
Yes, ProfSam.com.
Okay.
Thank you for joining this deep dive. Study well, practice your problems, and all the very best.